So, hi everyone. So I'm Leo Andres. I'm a PhD student at OCamlPro and LMF, working with Pierre Chambart, and this work is a collaboration with two other people from Lisbon. So my PhD subject is about comparing OCaml to WebAssembly GC, but I'm going to talk about something else today. So I'm going to talk about OE, which is a WebAssembly interpreter written in OCaml. So I started this just to learn and experiment with Wasm, and also to help my work on the OCaml to Wasm compiler, which was preparing many different proposals. And quickly it started to become much more than an experiment. It was testing the full test suite, which was covering a lot of stuff, but we wanted to try to test the interpreter more. So with an intern, Rick Patrizio, we wrote a grey box further using Crowbar, which is an OCaml library, and AFL. So the idea is that you write generators. You use a modified compiler to produce instrumentable binaries. And the instrumentation is going to guide the generator towards unseen path. And once we are able to generate a module, we do differential testing by comparing the result of our interpreter against the reference interpreter, or a version of OE that is doing more optimization to see if the optimization are wrong or not. So the way you do this is quite declarative. You basically use combinators from the library. So it looks like this. And the only tricky part is how to generate well-typed Wasm sequence of instruction. So you verify the stack types, and you look at it, and you see, oh, what kind of instruction I can use. You pick a random one, and you do this over and over. So it's unbugged in various places. So in the poetic printing, the type checker, and some overflow stuff. And then we wonder, okay, can we test the interpreter more? So there is two ways to do this, at least. So symbolic execution or abstract interpretation, but there is no tool to do this kind of analysis on OCaml code directly. Or you could rewrite this in code and extract it, but I don't want to do this. So we didn't go further on this part, but I will come back to this at the end. So what I'm going to give a quick introduction to OE. So if you have this module, nothing happens because by default you have no I/O capabilities in Wasm. So we did designed an API to be able to define a OCaml function like print I32, and with GIDT, which are lightweight dependent types, we disturb the type so that we don't get an error at runtime if the type is wrong, but at link time, which is not the case in most other interpreter, I guess. So that's how you use it. It's quite straightforward. Okay, we don't care. So it supports almost all standard extension except ACMD because it's tedious, and it also can handle some proposed extensions. So right now I'm handling the GC part. Yeah, and so in March we met the Carlos Santos in Dutch tool, and he told us, oh, you should do symbolic interpreter in Wasm with your interpreter, symbolic execution. So they came to Paris, and in 3 days we get something working, kind of. So just to recap, what's symbolic execution? So it's a kind of static analysis, also known as white box phrasing, where you use SMT formulas to test reachability. And so the goal is to find which input value can lead to a crash in the module, Wasm module. So how do you do it? You have to generate a path condition for each reachable branch. So if you have this PC initially, you make a comparison and you start with the result. So you add this part to the PC. Then you test the condition, and in one case you are going to add this to the PC, the condition equal true, and in the other branch false, and you are going to explore both. So how does it? So yeah, we use the binding mechanism that I showed just before to have this function, which allows to declare a value to be symbolic. So if you run this simple program, it is going to give you a model at the end telling, oh, if X is equal to C, then the program is going to crash. So for this, we ask the SMT solver a model at the end when we reach a trap. So the good thing about this approach is that it has no false positive. So usually people in the industry prefer this kind of tools. So the question was, okay, how can we implement this and also keep the concrete interpreter, because we don't want to change all the code or having to maintain two of them. Or another way to see how to make an interpreter symbolic if you already have a concrete one quite easily. So the answer is you put everything in a functor, which are parameterized module in kernel, and you use the choice monad. So this is how the interpreter looked like before. So you match on the instruction and on the stack, and you just interpret. Quite straightforward. So the first thing you have to do is you functorize over values. So you define a abstract type of values and some primitive operation on them, and you just replace by the new module parameter. So in the concrete case, they are just going to be what we had before, so concrete Wasm values. And in the symbolic case, they are going to be expression, like the one you saw in the path condition before. Then you have to functorize on the choice monad. So this is the signature of the module. And okay, so it provides you two things. So the choice.select and a bind that is hidden here in the star. And in the concrete case, the good thing is like it has no abstraction runtime cost, so we get the same performance as before, thanks to F lambda and the right inline invocation. And so in the symbolic case, what does select does? So what is the select plus bind actually doing? So in the concrete case, nothing, it's just the identity. So you can see this is doing as the previous version. And in the symbolic case, it's going to evaluate both branch. This is hidden in the star again. So how is it implemented in practice? It's basically the continuation and the state monad. The state contains the pass condition, and the select function here adds a condition or not condition to the PC, depending on which branch you are going to. And it called, also before doing this, it calls the SMT solver so that we don't evaluate both branches if one of them is not reachable. Sometimes we have to copy part of the state, and we do some expression simplification to avoid calling the SMT too much. And since like 1 month, we have a multi-core version of the choice monad so that we can evaluate branches in parallel. So to benchmark the results, so we compile C programs to Wasm, and we run the interpreter on it. And there is a competition called TestComp, where you have to find bugs in C programs. So we are reusing these benchmarks. So we have some optimization for malloc and free. And compared to Wasp, which was interpreter did by the 2 Portuguese guys that I talked in the beginning, so we are between 100 and 2,000 times faster. So we are quite happy about it. And now most of the time is actually spent in the solver. So the goal is to see how we can spend less time in it. There are many things we want to try now. So we are only compiling C programs to Wasm. We would like to do Rust, and then is actually starting to do this. And COBOL and C++, because we do COBOL at OCamlPro. Yeah, we could limit combinatorial explosion by having proper join points. That is like if 2 branches are going to be the same state at the end or same path condition, you can merge them somehow. Yeah, another PhD student found that guiding symbolic execution with the variant of A star on binary programs works quite well, and we want to try this technique here. Yeah, Pierre has an idea about adding a domain to propagate some simplification, and this is starting to look like abstract interpretations. Also, we would like to experiment with more solvers. So we did Colibri 2, which is a constraint solver, and also Altero, which is the OCaml SMT solver we are doing at OCamlPro, and CVC5. Probably experiment with JIT and try to see if we can do some Wasm to Wasm optimization thanks to the symbolic execution. And we would like to add support for exceptions, algebraic effects or step switching, and the full GC proposal, because we are not handling this right now in the interpreter. And the main reason why we would like to have the GC, because if you remember the question, how can we test the interpreter further than what we did before? So it is written in OCaml. And now we have few compilers from OCaml to Wasm GC, the one at OCamlPro and the one that Joe is doing. So with GC support, we could actually run OCaml programs in the interpreter. So basically what we get is symbolic execution or web threading of OCaml programs. And so we could find more about by interpreting the interpreter with itself. That's what I'm going to try to do at the end of my PhD. I'm not sure if I will have time, but we'll see. Yeah, probably not. Yeah, so the code is available here. It's open source, you can try it. So it can be used for debugging and experiments with Wasm, embed C in OCaml, or also Rust or whatever, once we manage to handle this. Perform static analysis on Wasm, find bugs in programs compiled to Wasm, so mainly C programs for now. And also some part of it are reusable, like the encoded library, which is talking to the solvers, which is developed by Philippe. And the choice monad, I think, can be made a separate library to the multi-core implementation of it. So that's it. Thanks. Yeah.
So you mentioned that now you're spending most of the time in the SMT solver. Is there any idea to use simpler solvers or custom solvers?
Any idea
to use a simpler solver?
Yeah, but you may not be able to manage our past conditions. So the idea is most likely try to call the solver less. It's not clear. We have some ideas, but and I'm not sure the other solvers are actually more performance. We are going to try.
I'm curious what kind of search or scheduling algorithm you're using. Is it just doing like a depth-first search, or is there some sort of heuristic-based approach?
No, I think it's a DFS for now. Yeah. Yeah, but that's what I say. We want to try A star at someone, a variant of A star because DFS, that's what we do, but it's not very, it's what everyone do and it's not working quite well.
Okay, thanks.
So you obviously, in the Symbolic case, make use of the ability to invoke continuation multiple times. Have you considered using OCaml's just effect handlers instead of choice monad?
Yeah, but it's not working because
you need to restart. What do you mean by restart?
Maybe we can do like dual microphones.
Yes, we need we might multi-shot.
Yeah, but I know somebody who did multi-shot for OCaml, and that guy's sitting right here. So I will be interested in talking to you if you. I will actually just be interested in the experiment and seeing what the time performance will be like.
Would be cool.
Yeah. Okay.
Anything else? Mm-hmm.
Just one question. Do you think that it would be possible to bring this method, so symbolic execution of WebAssembly files, to a status where you can generate test vectors, like LLVM is doing?
I'm not sure I know what you are talking about.
Can you repeat, Thomas? Generate what?
Yeah, so you know LLVM CLE, so KLEE?
I don't, but Pierre does. So.
This using the Step3 SMT solver, they can generate test vectors to do something like test vectors to get 100% of code coverage, for example, and they use a symbolic execution for it, as far as I know, and it's quite old. And I'm wondering if something similar could be doable with your approach. So having you give your tool a WebAssembly file, and it will generate test vectors.
So it's the case. The models that Leo shown on the slide earlier, it is a test vector.
All right. Okay. Then sorry that I didn't get it. Okay.